So today we've got Jerome Neufeld from the University of Cambridge with us. It's great to have you, Jerome. Could you, by way of introduction, kind of tell us a little bit about yourself, what your PhD is, and how you kind of found yourself working in carbon capture and storage?
Sure. So I came at carbon capture and storage from a bit of a long and circuitous route. I did an undergraduate in engineering science or physics, engineering physics. And then I went into geophysics and I studied how sea ice forms in the polar oceans. And it turns out that sea ice is a porous medium. And so I looked at experiments and some theory about how water flows through sea ice. And then as a postdoc, I came to Cambridge partially because I'd found out about some of the people working here to work on geological carbon storage from a fluid dynamics perspective. And from my perspective, it still had the same climate motivation that drove me to study sea ice in my PhD. And it had the same kind of physics. It was flow in a porous medium. And I found that actually there were a fascinating number of problems to do with flows in porous media that are very topical in terms of how do we think about carbon storage? Is it safe for the long term? How do we understand current projects? And so now I have very fortunately stayed in Cambridge and have a research group that looks at any number of these kinds of flow problems, a large portion of which is geological carbon storage. And that's of course what I'll talk about today. We also work on things like glaciers and polynyas in the polar oceans, and more recently, how you make a planetary surface, how you freeze a magma ocean. So I'm basically a fluid dynamicist now that looks at different geological problems. One of the big ones is carbon storage.
Oh, great. Yeah, interesting route to it. We look forward to hearing more about this today. So what we'll do, as we usually do, we'll take questions at the end. So Jerome will kind of talk through and give us a presentation first of all. If you have any questions that come up while Jerome is presenting, feel free to ask them in the chat, and then we can address these and pick these up at the end, unless there's something you want to touch on while you're talking, of course, Jerome. So
Great.
Hand over to you. Thank you for joining us today.
Great, thanks. First of all, thanks for the opportunity to speak to all of you and tell you about some of the work that's been going on with some excellent students and postdocs and collaborators over a number of years. You'll see at the bottom that we've been very fortunate to be funded in part by the UKCCSRC through EPSRC. We've also been funded to work on carbon sequestration by NERC in a consortium with Imperial College, Sam Creever's group in particular, BGS and Zoe Shipman's group in Strathclyde. And we're also involved in a consortium funded through BHP, the Australian company, which is a consortium between folks in Cambridge, Sally Benson's group at Stanford University, and Ralph Hess and Stefan Matai at the University of Melbourne, as well as the CO2 CRC, which runs the Otway International Test Center, which I'll show you a little bit about later in the talk. So we're trying to essentially build reduced models of the fluid dynamics of geological carbon storage. And the kind of questions that I'd like to talk about or ask and answer today are how do we secure the long-term storage of CO2? So really, you might want to think about this as, we know that we can do carbon storage. There are various places in the world where we have already done carbon storage. Here's a somewhat outdated map that shows some of the projects that are currently ongoing. And the question I'd like to ask is, how do we think about the CO2 that we put down there? Is it going to be stored stably? Is it going to stay relatively within the containment volume? What's the fluid dynamics that we need to think about? And should we, how do we reduce that risk? Because there's a cost associated with that risk. That uncertainty has to have some sort of cost built into the plans for any of these large-scale CCS projects. So I'm going to talk about really 3 projects today, 2 in some detail. I'll talk about the Sleipner project in the North Sea, between Scotland and Norway. And I'll talk a little bit about a project that's further in Victoria in Australia, further south in Australia, called the Otway project, which is an international test project. And just to give you a sense of the kind of things that we're thinking about, of course, we're thinking within the context also of geological storage in the UK. And the UK, by far and away, is one of the more fortunate countries, I would argue, because we have a huge plethora of potential storage sites, either in depleted hydrocarbon fields or actually a much larger number of saline aquifers. And the really helpful point here is that those fields are in the near offshore. You know, one of the questions that has come up, and people like David Reiner have talked very eloquently about this, is public perception and public acceptability of things like carbon sequestration. I think those questions are maybe not nearly so tricky if carbon sequestration is in the near offshore environment. And so the UK is, I would argue, very well placed to try out this kind of technology. Of course, here I'm speaking to many who will know many more things about this than I do, but just to sort of set the scale, recently Boris Johnson reiterated that carbon sequestration plays a role in decarbonization of the UK economy going forward, and we've moved beyond thinking about CO2 storage as something simply for coal-fired power plants. Actually, we're more thinking about things like bioenergy, cement, steel, that sort of thing. But the scale is huge. So here's, now this is an old graph, almost, I guess, 15 years old now, but it shows the sort of scale of projects. And I'll show you the Sleipner project, which is this green bar in the middle, which is a megaton of CO2 a year. That's a modest size. I'll show you the Otway project, which is very, very small volumes. The largest volumes are, of course, the blue bars here, which are typically in the States, enhanced oil recovery scenarios. So we have some expertise in injecting CO2 and trying to image and understand what's going on, but the volume of CO2 that you might want to inject is quite large indeed. So really what we want to ask from my standpoint, from a fluid standpoint, is we're going to be injecting very large volumes of CO2 potentially in the subsurface. And we'd like to do that in a cost-effective manner. And from the storage side, the main risks or the main costs are associated with the potential for that CO2 to go outside the containment volume. So how can we be assured that it'll stay there? And any other associated risks like pressure monitoring and management, which I'll talk about at the very end of this talk. Okay, so here's the sort of the basics of fluid dynamics of CO2 in terms of what should we care about. So the two key fluid dynamical properties that we need to care about are the fact that CO2 is less dense than the saline brine into which it would be injected. So you're injecting the CO2 typically down at temperatures and pressures where the CO2 will be supercritical, so it's more dense than the gaseous phase. It'll be more efficient to store it at great depths. And that's typically, for a typical geotherm, something greater than something like 800 meters depth. So the CO2 is less dense than the water or the brine, which typically fills the pore space. And so it will have a buoyancy force that causes it to rise. And so that's really the thing that we need to fight against in terms of trying to stably store CO2 over long time periods. And the second thing that I will touch upon at the end is that CO2 is less viscous than water, and that has implications for how we think about pressure management. It also has some potentially very positive implications for how we think about the mixing of CO2 and brine. And the reason why mixing between CO2 and brine is important is because of the trapping mechanism. So we've pumped in this buoyant fluid that's CO2, that's light compared to water. We'd like it to stay in the porous strata to which we've injected it, and it would like to rise up. And so what are the ways in which we can mitigate against the risk of the CO2 coming back out to the surface? And so there are a hierarchy of mechanisms which potentially trap the CO2 within the subsurface. And those are structural, so you might hit an impermeable baffle or a cap rock or a mudstone as given in this schematic. And that's the, as it were, the sort of the leading order trap. That's the one that we all think about, is that I'm going to pump the CO2 down beneath something that is just simply impermeable so that the CO2 can't rise up through it. And of course, that's certainly where the first large-scale CO2 projects have been trialed. But it turns out that we may not need to rely on either the complete and utter integrity of that cap rock, nor indeed on a cap rock at all. And that's because we have another set of mechanisms. One is residual, otherwise known as capillary trapping. So just like when you take a sponge, you dip it in the kitchen sink and you bring it out, well, lots of water gets trapped within the sponge because of surface tension acting on that water. In a similar way, surface tension acting between the CO2, the water, and the rock phase can trap the CO2 in the pore spaces of the rock. So that's one. And the second one is that you can dissolve CO2 into the water. Turns out that carbonated water, or CO2 saturated water, is dense compared to unsaturated water. And so that means that you now have relatively dense CO2 saturated water that will tend to sink. And so that's one way of storing the CO2 stably, is in the water phase. And of course, finally, and arguably most stably, you can turn it into a carbonate that can take fairly long time scales. So there's been this sort of idea that there are these four trapping mechanisms, and as the picture on the bottom left illustrates, there's an idea about when those mechanisms are really important and when they are relevant. And I'd like to explore some of those timescales and ask, is this the right diagram? Are some of these processes acting faster or slower than we might otherwise have thought? And the key piece that I'm going to try and inject, pardon the pun, throughout this talk is that the geological setting is crucial to understanding how these processes work. And that's because geology is complicated on many length scales. So here I've got a very nice diagram showing geological complexity from the pore scale. So that's at the microns, the tens of microns scale of the individual pores in which the CO2 is in place. At the core scale, that's the scale at which folks like Sally Benson or Sam Creever can measure the flow of CO2 through actual rock at reservoir temperatures and pressures. And we know that already at the core scale, we can see significant heterogeneities. Then there's the log scale. So at the sort of tens of centimeters to meter scale, there's geological complexity and heterogeneity, which we can only see through sampling at boreholes. It's virtually impossible to see seismically, at least at significant depth. And then there's the outcrop scale. And at the outcrop scale, there's even yet larger complexities at the sort of 10-meter scale. And this is now the scale that we're starting to be able to resolve seismically with a typical quarter wavelength resolution of, say, 10 to 15 meters. And then there's the field scale at which we'd actually like to be able to predict whether the CO2 is stably trapped. And so I'm going to talk about some processes that take us all the way through these scales and how do heterogeneities impact the trapping processes across those scales. So the first thing I'm going to talk about is really a very quick run through of the Sleipner project. This may be familiar to many of you. To me, it presents a way to talk about the sort of the archetypal structural trapping. You know, the Sleipner project is, in my view, the sort of the first project you go to try and understand CO2 sequestration. And of course, it's the ideal setting. It's in the North Sea. It's associated with a natural gas production facility where they've already extracted the 10% CO2 from the natural gas stream. So the economic cost is already covered. Instead of venting it to the atmosphere, the $55 a ton tax on offshore CO2 emissions from the Norwegians is an incentive to instead drill this long deviated well and to pump the CO2 in. And so at the Sleipner project, they've been pumping about a megaton of CO2 into the Atsira sand formation, which is about a 200-meter thick sandstone, which is underlain by the most extensive cap rock you can imagine, the Nordland Shale. And so this is the ideal place to start thinking about carbon sequestration. You also have the advantage that you can see what's going on. So as illustrated in the previous slide, because there's the natural gas field, the natural gas pays for the seismic surveys that come by, and those seismic surveys have come by fairly regularly since 1996, observing where the CO2 has been injected. And importantly, they got a pre-injection survey. So if we look at that, this is now looking in two-way travel time. So this is the time it takes the seismic signal to go from the ship down to the reservoir and back up to the receivers along the receiver array. So that two-way travel time you can think of as depth, given the velocity model for the shallow subsurface. And on the left, you see before the injection, and on the right, you see after the injection. And so this gives you some semblance of where you can see the CO2 within the formation. If I color that in, or I should say, if Lawrence Coton very carefully colors that in, you can see both the boundary with the overlying Nordland Shale. You can see this yellow band, which is the Otsira. The injection point is roughly marked on here. And then on the right, you can see what are the layers of CO2 rising up throughout the formation. And already you can see geological heterogeneity playing a role here. So on the left, it's not completely clear in the pre-injection seismic survey what the structure of the geology is in between the injection point and this Nordland Shale unit. Obviously, the CO2 being a fluid that is very sensitive to the rock properties, discovers or finds that there are these thin interbedded shales that give rise to what has been classified as 9 layers that the CO2 rises and spreads out at it. And so understanding how you would characterize and in fact predict in some sense this geological complexity is one of the challenges I think in understanding or predicting the influence of heterogeneity on large scale carbon storage. So just to give you a sense of the Sleipner project, here's the seismics from 1994 all the way up to 2008. You can see the bright reflections from each of the layers of CO2. Those are marked out or traced in Fran Boett's work on the bottom. And if you look down at the top, you get to see something of the plan view of the plume. And what you see is the plume rises. As it hits each of these thin interbedded shale layers, it spreads out. Some of it leaks through, spreads out. It gets up to layer 9, and at layer 9, it's hit the Nordland Shale unit, and there's no seismic evidence, at least, that the CO2 has made it beyond that Nordland Shale unit. So it does seem to be a competent reservoir as predicted. Now I want to go a step further to think about the fluid dynamics, and just as a little bit of a side note, Lawrence Coton did some very careful seismic imaging. It turns out that from these images that I show you here, which are just showing you the amplitude of the seismic reflection, you can see where the CO2 is, but you can't say the volume in any given layer. And if you don't know the volume over time in any given layer, it's really hard to build a fluid dynamical model of how that CO2 is spreading. People have tried, and it's quite difficult. You have too many unknowns. What Lawrence did is he went back to the top layer and he said, well, I can measure 2 things. I can not only measure the seismic amplitude, but I can measure this subtle phase interference between the seismic signal bouncing off the cap rock and bouncing off the cap rock with a lens of CO2 underneath. And so here's the difference in two-way travel time between the pre-injection survey in 1994 and the 2010 seismic survey. And you can see that there is a faint difference, a phase lag, between those two associated with the ponding of CO2 underneath that cap rock. And of course, you also have the amplitude. Now you have 2 pieces of information, and it turns out that you can correlate those 2 pieces of information. And what Lawrence did was took the change in two-way travel time and the amplitude of reflection, and he plotted those against each other. And there's a nice little theory about how those wavelets interfere with each other as you get an ever-thinning CO2 plume. And that lets you invert for the thickness of the CO2 plume, even though the thickness is below the quarter wavelength resolution. So quarter wavelength resolution is about 15 meters. Here we're trying to resolve the CO2 plume down to something like a meter, meter and a half thickness. So with that seismic trick, we now get the piece that is truly exciting from a fluid dynamicist standpoint, we get the volume or the thickness of CO2 as a function of time. And so here you can see from 1999, so this is after injection started in 1996. 1996, you recall, injection starts at the base. It's got 200 meters to go up through this complicated geology. We start to see it in 1999 at the boundary with the Northern Shale. And from there, it spreads out. And it has this very peculiar structure where it spreads out and makes, I don't know, a guitar shape, right? It's got a long northward going spine that races off to the north and then starts to pond out at the top. We now have the thickness as a function of time, so we have the volume as a function of time, and that then gives us the input that we need. So we now have a single layer, we know the volume that's going in as a function of time. Now can we understand what's going on? Right? This is, as it were, a measurement of the structural trapping process as a function of time and the complications behind that. So in this picture, I guess Lawrence has taken a cross-section just to give you a sense of how that CO2 plume builds up as a function of time. The bottom is that seismic cross-section. You can see this region sort of at 600 meters range where you don't get a seismic reflection, and this is so-called seismic chimney that people like Gareth Williams have thought about at BGS. It's where you have continuous CO2 all the way down, and so you don't get a seismic reflection. So this might be the feeder channel, and you can see that if that's the feeder channel, the CO2 is essentially rising up to the caprock. You can see the caprock in the top diagram, and it's flowing uphill, kind of like you'd imagine it should. So now we have a process where buoyant CO2 is rising up, it's hitting the caprock, and it's now trying to fill out that bowl, that space, and we can ask how it does so. So here's the caprock topography shown on the left. It's essentially an anticlinal trap. So it means there's a bowl at the bottom. There's a trough that goes up to the north with a much larger bowl. It also turns out that this is the geological depositional environment here was one in which it looks like there's an old riverine channel, which is deposited a different kind of strata through this sort of sand wedge. And so we're going to take the simplest possible model. We're going to say that there's one kind of permeability outside K1. There's a sand wedge which has a thickness W and a second permeability K2. So how does CO2 flow in such a setting? So now here, there are sort of two things we should think about. And you can think about this like pouring honey on toast, if you like. It's the porous medium version of that. If we have CO2 spreading, it'll spread under its own weight, just like if you have your toast centered on the table, the honey will spread out under its own weight. And so that's one contribution. The second is, of course, it'll flow upslope. CO2 is buoyant, up it goes. And of course, in my house, the kids, if they're holding the plate, don't hold the plate straight. And so the honey runs off the toast, right? And that's the only two things that you really need in a model of how the CO2 spreads. For those who are interested, the model is at the bottom, and I can certainly answer questions about that if you're interested. So how does that model work? Well, we can run that model because it's fairly simple many times. And so this is one of the styles of approaches that we've taken to these kinds of problems, is to write very reduced models. We're only interested in the thickness of the CO2 plume. We've averaged all the properties over their depth. We can average the saturation if we need to. We can average over different permeability structures. And then we can run a simulation of 20 years of injection history at Sleipner in about 2.5 minutes on a desktop computer. And that means that we can span a huge range of parameter space. The reason that's interesting, or the reason that's useful, is because we don't know what the geological heterogeneity is. The leading order problem in trying to understand the manner in which CO2 spreads in the subsurface, I would argue, is that we have point measurements and coarse point measurements of the geological structure and complexity. And so we need to average over there in some way. And so here's just to say that we can run this model hundreds, in fact, thousands of times and span the parameter space to try and get the best idea of what the reservoir properties are using that kind of simplified approach. And we can run it forward. And so this is the future predictions for Sleipner. At Sleipner, we do think that a lot of the CO2 will run to the north towards that much larger anticlinal dome. and their structural trapping will play the majority of the role in trapping the CO2 in the short term, right? I'll come back to the role of pressure, but pressure doesn't play a role at Sleipner because that Utsira sand formation is so thick and so permeable. Now, structural trapping is, as it were, one of the ways in which you might trap CO2 in the subsurface. I mentioned two other ways already. One is trapping by surface tension. So that was the water held into the kitchen sponge example. On the left is some micro-CT measurements by Sally Benson at Stanford. These are actual measurements of CO2 within a core volume being trapped within the pore space. The diagram on the right is a very helpful movie by Chris McMinn, just showing with these simple models, if you have a constant volume of CO2 spreading up slope, as it moves through the pore space, it leaves behind a residually or a capillary trapped portion of CO2. And the important thing about capillary trapping is that you need to leave, you need to have the plume leave that area so that you can leave some CO2 behind. That's somewhat different than the bottom case. The bottom case is trapping by dissolution. And in trapping by dissolution, again, you dissolve the CO2 into the water. That makes the water heavy. And so here's the sort of the animation or the simple theoretical prediction from Chris McMinn. On the bottom is some laboratory experiments where we have a fluid that is buoyant, which when it mixes with water makes something dense. And so that mimics this role of dissolution into the water, which then causes that dense water to sink away, and it eats away at the volume of the buoyant CO2. And so both of those ways can act. And the question is, how fast do they act? So the first thing I'll talk about is capillary trapping, because it's certainly one of the archetypal ways of trapping CO2 in the subsurface on fairly quick timescales. Effectively, you just have to turn off the tap. The CO2 will continue to spread under buoyancy, but as it does so, it'll be residually trapping CO2 as it goes. And one of the places where we can see this actually happening is at the UKCCSRC Autumn Web project. So here it is, about 2.5 hours drive from Melbourne. And if we ever get to travel again, I would highly recommend that you go and visit the site. It's actually one of the more interesting CO2 sequestration sites I've had the pleasure of visiting. But the particular piece of science that I think is relevant to the capillary trapping problem is their stage 2C experiment. And they've done a number of experiments, and they're on experiment 3 now. They have a natural source of CO2, which they extract. They then pump in. The stage 2C experiment was 3 lots of 5,000 tons of supercritical CO2 each into the Parati formation at about 1,500 meters depth. And they have a continuous or active source seismic network laid out in really quite impressive detail on the surface, which they can monitor that plume. And what they see from this 3 staged injections of 5,000 tons of CO2 each is that you get a plume which spreads, and then after about 2 years, seismically at least, that plume seems to have stopped spreading. And so that seems to be a direct observational evidence that capillary trapping has indeed immobilized the plume and managed to trap it within place. So again, you can run different kinds of numerical models. This is again that simple model that I showed you for Sleipner, but the only difference now is we inject a fixed volume, and as you see on the bottom here, that fixed volume spreads, and as it moves, it leaves behind a residual amount of CO2, and so over time you're left with less and less mobile CO2. And these calculations are courtesy of Kieran Gilmore and Adam Butler, with many thanks to the folks from the CO2CRC for the inspiration for these calculations. The effects of capillary heterogeneities on plume propagation can also be felt at different length scales. And here, I think we've been really intrigued by the recent work coming out of, to some extent, both Sally Benson's group and Sam Creever's group at Imperial College. So there, they've been looking at core scale heterogeneities, doing in situ temperature and pressure measurements of CO2 flooding through a water saturated core. And what they find is that if you have heterogeneities within the core that give rise to capillary pressure or wettability gradients of the CO2 within the rock, I guess the water within the rock in this case, you can drive heterogeneities dynamically within the rock, and that gives rise to different flow curves. So if you're really pushing things through, the rock looks, as it were, relatively homogeneous, but as you start to dial back the flow, the heterogeneities, the ability of the CO2 through its surface tension, its capillary forces, to be able to find the heterogeneities in the rock becomes more and more important. And we've been starting to think about exactly that kind of problem with Graham Benham and Mike Bickle. And more recently, Sam Jackson and Sam Creever have shown that that can have quite an influence on how the CO2 is distributed as it flows. And here you can see 3 different kinds of patchy heterogeneities and the influence between either the homogeneous type flow or this capillary heterogeneity aware flow, how that plume migrates. And it can have quite an impact in terms of how patchy the saturation is, how localized the flow is within the reservoir. And so that's, I think, a very interesting question, because it has implications for, given a certain volume that you inject, how far does that volume extend? It depends on how it samples the heterogeneities, whether it flows down just the high permeability streaks, whether the capillary heterogeneities cause it to be widely distributed, very patchy, that sort of thing. It also has an implication for the next process. And so the third, I guess, trapping mechanism that I talked about was solubility trapping. And so the distribution of CO2 definitely plays a role in the efficiency of solubility trapping. Just to really nail it home, supercritical CO2 and brine are immiscible. And pure CO2 is, of course, much less dense than the brine, as shown on the picture on the top right. So here's the density of CO2. Here's the density of the brine. But as you increase the CO2 content in the brine, you get to an even higher density. So the density of permeable water is more dense than the density of fresh water, as it were. And this means that you can drive convection. So here on the right is actually a laboratory experiment in a Healy-Shaw cell, so a very thin cell that mimics a porous medium, but gives us fantastic optical properties. We are not using CO2, we're using an analog again, which is water on the bottom, propylene glycol on the top, which is buoyant, but as you mix the two, you get something that's dense. And that density on mixing drives the flux of the top fluid down. So it would be driving the convective dissolution of CO2 in exactly that kind of setting. So we can ask, is this relevant in sort of real world settings? I think one of the most impressive papers on this is by Mark Hess and co-authors, looking at a natural CO2 setting. This is Bravo Dome in New Mexico. And this is a fairly large and extensive setting where volcanically derived CO2 has been placed into this natural field at about 700 meters depth. And we know that those gases were placed somewhere between 1.2 to 1.5 million years ago. And their estimates are that roughly 40% of that CO2 dissolved during the emplacement, followed by a further 22% dissolving over the subsequent 1.2 million years. And that 22% subsequently is more than you would expect from simple diffusion of CO2 into the brine. So there are sort of two puzzles here, and we'll return to both of those. One is that as the CO2 is somehow making its way into this natural aquifer, this natural reservoir, that process of putting the CO2 in and placing the CO2 has caused it to be to mix and to dissolve at a fairly high rate. And the second is that subsequently that CO2 has dissolved over a much longer time scale. And to give you a sense, the total mass loss through dissolution is about 366 megatons of CO2. And so if we can understand the processes of the dissolution in these kinds of settings, can we engineer it to enhance it and therefore further stabilize CO2? So let me just give you some analogues again. So again, this is a CO2 analog. In this case, it's glass beads filled with water. That CO2 analog is light compared to the water. And so it will want to run across to the right. But as it does so, it'll mix, and the mixed product is dense and so sinks away. And so the volume of buoyant CO2 decreases as a function of time. And so if, oh, maybe my movie doesn't play today. That's too bad. No, can't find my cursor on Zoom. Sorry. You get the stills instead. So if you look on the right, this is with dissolution. You have buoyant CO2 that is spreading off to the right, or buoyant CO2 analog that's spreading off to the right. It's mixing and dissolving, and so the dark blue patch, which is really the buoyant CO2 analog, is getting smaller as a function of time. You see that you only make it to a finite distance from where you've released it, whereas the equivalent on the left, which is, in fact, the left is just salt water and fresh water, which doesn't have this dissolution process. That plume runs forever, as it were. And so we can make simple models, and this is something that Chris McMinn did very effectively, where you can see that the current first spreads, and then as dissolution really begins to play a very strong role, it eats away at the mobile volume, and so that shrinks back. The simple theory is the light blue curve, and you see that it's relatively symmetric. It spreads, the extent, xn spreads as a function of time and then symmetrically comes back. The laboratory experiments pleasantly are much more complicated. They take a lot longer to retreat, and that's because you can build up the saturation of CO2 in the water. And so Duncan Hewitt here wrote a very nice paper where he numerically solved for the dissolution into a finite volume. And here you see that the ambient concentration of CO2 builds up until you reach this shutdown regime. And now the rate at which CO2 dissolves is getting smaller and smaller as a function of time, because the concentration, the average concentration of CO2 in the water is increasing as a function of time. Okay, so that's some idea of how the dissolution might work if it's actually convectively dissolving. But of course, that only is going to be the case for very large aquifers or very permeable aquifers where you can actually drive convective style flows. But there were two pieces to the puzzle in Bravo Dome, and in fact, more dissolution occurred during the emplacement. And so recently, Kieran Gilmore has been thinking about emplacing CO2 not into a homogeneous medium, but into a very much more stratified or layered or heterogeneous medium. And we're taking here, as it were, the simplest archetypal heterogeneity we can think of, which is just a single high permeability lens. And what Kieran has shown is that if you inject CO2 into that sort of high permeability lens, you get two kind of modes. Initially, you have essentially an advective spreading of the CO2 along this lens, and the length of the CO2 finger in that high permeability lens increases simply at the rate at which you've injected. And subsequently, the diffusive losses, and the diffusive losses are to the surrounding low permeability material, and they are diffusive, but they're along an extending interface as this finger progresses. That diffusive loss can get comparable to the amount that you're injecting at the interior. And so the length of the finger, it doesn't grow nearly as fast as a function of time. And as you can see, the fraction of CO2 dissolved gets really quite substantial. So we can go and apply these kind of ideas now to different kinds of experiments. And I think these are relevant to things like measurements from the Frio injection experiment in Texas, where there was an injection well and an observation well. And in both cases, and also to the Salt Creek field in Colorado, which Mike Bickle has measured. And both of those see both the CO2 front coming through and the evidence of CO2 dissolving into the formation fluids as a function of time. And so the question is, how much CO2 has actually dissolved into the formation fluids? And is it, if it's been channelized along these heterogeneities, and so we have much more surface area between the CO2 and the water, is that dissolution rate really important? And so Kieran, thinking now specifically about the Salt Creek example, has thought about CO2 going along a number of these impermeable layers. And the answer is that within the first year or two, you can dissolve something like 8 to 10% of CO2, depending on the width and the permeability difference of these high permeability lenses. So in fact, it seems both from these historical measurements at Bravo Dome and from looking at the data from some of these more recent injection experiments that the dissolution rates, both on and placement into a heterogeneous medium, into a heterogeneous reservoir, but long-term can be really quite substantial and can lead to stabilization of the CO2. I should add that there's another feature to this problem, is that the CO2 is, of course, less viscous than the brine, and there's a well-known instability called the Safman-Taylor instability, in which the CO2, which is less dense, is pumped into the brine. Here we're traveling with the interface, as it were, so it looks like things are traveling to the left. But what you see is that depending on the number of layers, you can get a huge array of fingering and mixing between less viscous CO2 and more viscous brine, and that's something that Japinder Niger mapped out in some detail. And of course, there's also the interaction between that and density differences. And so CO2 is light, and so will run along high permeability layers, but then might find itself beneath dense brine. We can mimic that in the lab, as Chinendra Sahu has done, with a layered porous medium, here with a dense current flowing along the bottom that overrides into high permeability streaks, all of which increase the mixing. And as you increase the mixing rates, you increase the potential, at least, for this dissolution process to take place. So whereas we used to think that dissolution was either diffusively driven or principally convectively driven, actually I now think that it's the heterogeneities within the geological medium that are really going to dominate the signature in terms of the rates of dissolution. Okay, I want to leave you with, at least from my standpoint, some of the interesting and outstanding questions left in terms of how would we secure long-term storage, and what are the challenges. One of the challenges that I haven't really touched upon here, but certainly is an important one, is how do we manage the pressure in the subsurface? Right? If we already have water filling the aquifer, and the aquifer is not too large, too laterally extensive, or it has a low permeability, then in fact the pressure required to push the CO2 in and push the water out of the way to make room for the CO2 can be substantial. And so we need to think about schemes like pressure management. That's not such a concern underneath people's houses, as it were, if we're sequestering in the North Shore, the North Sea, but it does raise an interesting question about how exactly do we manage pressure. And one of the interesting places we can see that is in the Insala gas fields in Algeria, where a number of people have measured very interesting uplift patterns associated with the injection of CO2 at about 2 kilometers depth. Of course, just to clarify, that's a couple of centimeters of uplift over tens to hundreds of meters to kilometers worth of lateral distance. It's not something you could see on the surface, but it is something that you can measure from INSAR measurements of the desert floor. And they tell you something about the pressure at depth and how that pressure is propagating, which is interesting. So I'll leave you with the following outstanding question. I've showed you that there are a hierarchy of trapping mechanisms, and in fact that they can act rather quickly, potentially much more quickly than that diagram that I showed you, or that schematic that I showed you at the beginning suggests. Of course, structural trapping is the first thing that we often reach for. We're going to store CO2 underneath an impermeable cap rock. But it turns out that we can use the underlying geological complexity or heterogeneity to increase both the solubility or dissolution trapping of CO2, the dissolution of CO2 into the water, or indeed the capillary trapping of CO2 into the water. And I think there's great potential for utilizing those in much more unconventional settings where we may not have or may not be able to completely rely on such an extensive and impermeable cap rock. So I think I'll leave it there. I'll make one more analogy. Something that I like to sometimes say to my students or postdocs, I think as a sort of an outstanding challenge, geological heterogeneity is like turbulence is to weather models. In weather models, we never model weather at the scale of the turbulence, which is down at millimeters, centimeters scale. We'll never model the geological complexity over a reservoir scale down to the pore scale. We need to think, how do we upscale it past that, that turbulence scale, the complexity scale within the geological medium? Okay, I'll stop there. I'd love to take some questions.
Thank you, Jerome. So feel free to use the chat, or if you want to raise your hand or unmute yourselves to ask a question. I think we've got a question in the chat from Kevin Dale. Do you want to, are you there, Kevin? Unmute yourself and ask your question.
Oh, hi there. Thanks a lot, Jerome. That was great. At the beginning of your talk, you mentioned mineral trapping, and at the end, on your conclusion slide, you mentioned mineral trapping. Something I've heard about is using basalts, non-porous rocks to trap CO2, which seems quite a mystery to me, but I guess they must be carbonates or something like that. I wonder if you can speak to that a little.
Yeah, a little. So my knowledge of the geochemistry on mineral trapping is woefully less than it should be. But certainly there are places, and the basalts in Iceland is a really a characteristic example where precipitation of carbonates is thought to be the sort of a leading contender in these very basaltic systems. Essentially, all of Iceland is fresh basalt, and so I think it's CarbFix is the project which is operated there very successfully. People have thought about putting CO2 into ophiolites, which are also highly reactive. The interesting questions, at least from the fluid perspective, which seem to have been more or less overcome in Iceland, are if you're going to actually be precipitating out mineral within the pore spaces, you decrease the permeability as you permanently trap the CO2. So as you pump in more CO2, if it reacts with the rock, of course, it's going to start to clog up the rock, and you'd like to be able to continue to inject. In Iceland, they've injected into an extremely fractured basalt, and I think that really has helped that sort of process quite enormously.
Can I come back on that?
Sure, go for it.
Why basalt? Could it be other basic igneous rocks as well? What's special about basalt that people are interested in?
That I'd have to pass on. I mean, I think in general, most of the rock reactions are so long-term that it's really mineral. The reason why mineral trapping is usually at much later times on those plots is because for most rocks, the reaction rates are really very slow. Basalts, it's much faster. But more than that, I'm a little bit out of my depth there.
Thank you, Kevin. I think we've got a question from Sean McQuaid. Sorry if I pronounced the name wrong. Do you want to ask your question, Sean?
Yeah.
Hi, yes. Thank you very much. A fantastic talk. I really enjoyed that, Jerome. One of the things that concerns me is the amount of volume of CO2 we're sticking in the ground is going to be enormous if it does get if it goes into the ground and get off the ground. That implies that we may well have a lot of saline to manage on the surface. What does that mean in terms of strategies, in terms of thinking about, if we try to sort of optimize the different trapping mechanisms, does it have an impact on what we would do with respect to water management?
Yeah, so I mean, there's a whole suite of answers to this one. It's an excellent question. I think it really is where a lot of thought needs to go next. I mean, I think one dodge, which I think I brought up at the very beginning, is in the UK, at least from a public perception standpoint, we're always going to do this offshore, right? Pressure management is one of those things where the volumes of CO2 that we'd like to inject, of course, are going to be significant. And if the strata is, if you don't have the 200 meters thick zero formation, then actually what's the pressure that you're injecting that CO2 into the system is significant. And you'd like to, of course, minimize any chance of any sort of induced seismicity or anything like that. That being said, there are locations like Sleipner where pressure management will never be an issue. It's so big and it's so permeable that you would have to pump at an incredibly fast rate to raise the pressure to any sort of level. So that isn't the issue. I think if I just sort of hone in on your question about how do the different trapping mechanisms interact with the water management, there is an interesting one, and it is also one that has been done to some extent in Iceland, right? If you want a really stably trapped system, you dissolve the CO2 into the water. And so, one of the things that you might want to start thinking about, and in Iceland, they thought about it by bubbling CO2 down into water within the injection pipe, so that they're injecting CO2 saturated water. One of the things that we can think about is how do you enhance the mixing within geological heterogeneities so that you've managed both the water that's in there and the CO2. But I think absolutely this question about pressure management is a big one. How do you put large volumes of water in or CO2 in? What happens to the water is crucial. I think the one other thing I'd say is that, it's not we have plenty of other natural systems where we get lots of movement in the porous crust. To me, one of the more dramatic measurements I've seen are some of the essentially breathing of the Earth's crust as water flushes in and out of groundwater aquifers. And so I think, if you think from that standpoint, there's actually some room to put the CO2 in to monitor or to mitigate against the pressure. It then becomes a question about how many injection points do you have, that sort of thing. It's a bit of a wandering answer to your question.
Thank you.
Thank you, Sean. So do we have any final questions at all for Jerome? I've not seen any more in the chat, but if anyone's got any more questions, feel free to ask.
All right.
There we go. There's one. Catherine Daniels, do you want to ask your question?
Oh, hi, Jerome.
Hello.
I was wondering if you thought about the effect of reservoir depletion on subsequent reinflation of reservoirs in CO2, and whether changes in pressure in the reservoir would ultimately deleteriously affect the cap rock, which you might then be hoping to store CO2.
So you're thinking, that's an interesting suggestion. So re-injecting into like under pressured reservoirs. Yeah. I think, actually, I think this is a fantastic suggestion in terms of the pressure management. My own view is that, most of these reservoirs are at more than a kilometer's depth. And that even if the process of pressure depletion followed by reinflation causes some small scale pathways through the immediate cap rock, I find it, and I'd love to do the field experiment, I find it hard to imagine that CO2 would leak all the way to the surface. With a kilometer worth of geological complexity, the trapping mechanisms are so fast and so efficient that I think that it's unlikely that you'll get anywhere near the surface. But again, that's one of those things you'd like to test. That's an interesting suggestion about depleted reservoirs in terms of pressure.
Thanks,
Thank you, Catherine. So I think if we've not got any more questions, probably a good point to leave it. So thank you for joining us today, Jerome. It was really interesting.
Thanks.
Really a really in-depth look at that. I really enjoyed that. So just to update everyone on what we've got coming up next week. So next week we'll be hearing from Bryony Livesey, and she'll be giving us an update on the latest from the ISCF challenges. So we'll be hearing from Bryony next week. But yeah, I just want to say thank you once again, Jerome. That was really interesting. So thank you for joining us today.
Good. Thanks, everyone.
Thank you, everyone. Thank you. Thank you. Bye-bye.